Welcome to another video. So today we're looking a bit about organic chemistry, right? So organic chemistry is basically a section of chemistry that deals with compounds that have a carbon and a hydrogen atoms, right? So these compounds exist as carbon and hydrogen and sometimes have other basic atoms, but primarily they have to consist of carbon and hydrogen. All right, so two terms that we're going to look at is the functional group or the homologous series. So the functional group is a unique atom or group of atoms that gives a compound similar properties, right? And then our homologous series is just a series of compounds that are in the same functional group. So let's look what we're talking about. Right? So our homologous series, right, exists like we have alkanes, alkenes, alkynes, alcohols, carboxyl acids, and esters, right? So these are our functional groups, right? Now the functional groups for alkenes, they just have a single bond between their carbon atoms, right? So it doesn't matter how much carbon there is, it's just single bonds right through. For alkenes, there are double bonds, just one double bond present, and alkynes have one triple bond present. Alcohols have a OH in their formula, and carboxyl acid has a COOH, as well as esters that have a COO in there, right? So we're going to actually look through each individual separately. All right, so let's start with alkanes, right? So these, before we go to alkanes, these prefixes are going to be important in actually naming the compounds, the compounds under these series, right? So it doesn't matter which group you're in, they always start, the one here represents that it only contains one carbon. If it's one carbon, then it's a meth, right? If it's two carbon, it's eth. 3 carbon, prop, 4 but, right? And it continues like that. So let's look at alkanes and see how best it works. So alkanes are known as saturated compounds. The reason for this is because they contain the maximum number of hydrogen atoms, right? So there is no double or triple bond, so it only contains carbon and hydrogen, right? So it has single bond between the carbon, right? Its general formula, which is important, is CnH2n plus 2. Now the N represents the amount of carbon atoms, right? So let's say you wanted to know what's the formula for an alkene with 3 carbon, right? So N will be 3, so it's C3, and then H 2 times 3, which is 6, plus 2 gives you 8, right? So that's how the formula works. And then naming of the compound would be the prefix plus ane, right? So because it's an alkane, all their names end with an ane. Let's look at an example: methane, hexane, propane. So we know that meth or meth comes from 1. So we only have 1 carbon. So that means the N here will be 1. So that's C1H, right? And then that's 2 times 1 plus 2. So 2 times 1 is 2, plus 2 gives us 4. So that shows us that methane has a formula of CH4, right? And then for hexane, so we notice that the prefix here is hex. Hex is 6. So that is C6, right? CN6. H, we have 2 times 6, which is 12, plus 2 gives us 14, right? And then we have propane, so therefore the prefix here is prop, and prop is 3, so that is C3H, and is 3, so H 2 times 3, which is 6, plus 2 gives us 8, right? So that's the process of finding the formula for each alkane, right? So we're going to look at the structures, but before we look at that, we're going to actually look at situations where we have branches, right? And those branches have names, right? So we only focus on the first 3, even though sometimes we only use the first 2 at this level. So if it's a CH3 branching, then it's a methyl. So all we're doing is just minusing 1 from our formulas for the alkenes. So methyl is CH3, ethyl is C2H5, and propyl is C3H7. So let's look at what we just did in terms of their structures. All right. So let's go. So we're going to draw the structure of methane. All right. So we know that methane consists only of one carbon, right? And note that carbon has 4 electrons in its outer shell, and hydrogen has 1. So all these 4 will actually bond a single bond with hydrogen. So that gives us methane. All right. So let's look at hexane. So hexane has 6, right? So all we do is to draw 6 carbon. All right. So remember, they are alkanes, so each carbon-carbon bond is a single bond. And then we fill out, right? So if you don't want to get confused, what we can do is we cover, so we're focusing on this carbon here. So we notice 1 is already filled, so we have 3 more to fill, right? And those 3 will be filled by hydrogens. All right, so we're finished. So now we have 4 bonds going from that carbon. And then we can cover this one and this one. We notice there's 2 already used, so we need 2 for this. All right, so we get 4. All right, then we continue like this. So that's 2, so we need 2 more hydrogen here. That's 2, so we need 2 more. That's 2, so we need 2. And then that's 1, so we need 3. Right? So if we notice, we have 6 C's, right? And then with 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 H's. All right? So this is our molecular formula, right? And sometimes it acts as for our structural or condensed formula. So your condensed formula for hexane would be exactly what they are. So we start off here. So we have C. So we have 1 C there and 3 H's, right? Then here we have a C with 2 H's. And then here we have a C with 2 H's, right? And here we have a C with 2 H's. Here, same thing, we have a C with 2 H's. And then lastly, we have a C with 3 H's. All right? So our condensed formula tells us exactly at each carbon how much hydrogen is present. All right? So at the first carbon, we have 3 hydrogen. Second one, 2. And it continues, the last one is 3. All right? So these are actually just the unbranched structures of alkenes. But alkenes can exist as branch structures, right? And branch structures mean that it's going to actually get a branch off the long chain here. All right? So let's look at an example. So let's say we have this, all right? So we're going to fill out with our hydrogen. All right, so we notice at this point we have something that's going straight, a long chain, but we have something that's not just going on a long chain there, right? So a long chain doesn't mean a straight line. It means you're moving from one to the next and you continue, so it goes through all, right? But in this, if we start here, 1, 2, 3, if we go down here, we cannot come back up here, right? If we go 1, 2, 3, 4, 5, we can't reach this one. So here we have a branch somewhere on it, right? So always, if you count continuously, you're always going to miss 1 or more. All right, so let's go in naming branch compounds, right? So in naming the branch of an alkene, we first have to count or get the longest chain. And remember, the chain would be if we start moving from carbon to carbon, right? Which point we stop at that, so the longest one continuous, right? So if we go 1, 2, 3, 4, right? we only can stop here. So that's 4. 1, 2, 3, 4, same thing, right? But if we go 1, 2, 3, 4, 5, right? So we get a 5 chain. So that means we can, this would be our long chain, right? Now the next part is, once we identify the long chain, we're going to actually look at the point. We start counting the carbons to the point that is closest to your branch, right? So the closest one to your branch, right? So it means because it's 5, at each point we start here, we get 3. If we start here, we get 3. So it doesn't matter for this example. So this we're going to do 1, 2, 3, 4, 5. Right? So our branch is on the third carbon. Right? So let's look at the branch now. So the branch is CH3. CH3 has a name of methyl. Right? So in naming the compound, we first identify which carbon it is on, which is 3 hyphen the branch name, which is methyl, and then the name of the chain, the long chain, right? And remember we have 5 and it's 5, so that's pent, and they're all single bonds, so that is pentane. Right? And that's how you name any branch chain of alkanes. Right? So and that's it for alkanes, right? In terms of their structures and their names. So let's look at alkanes now. Alright, so let's go with alkenes, right? So alkenes we know have a 1 double bond with 2 carbons, right? Their general formula is CnH2n, and their ending of names ends with ene, E. Alright, so let's look at, go with ethane, right? So in this case, the F would be the simplest alkene because we have to have a double bond between 2 carbons, right? And if it's meth, then we don't have a double bond between it, right? So we're going with the simplest one, which is ethene, right? And we know that it has 2 C's, right? So the N is 2, and then 2 times 2 gives us 4, right? So the structure of this would be C double bond C, right? And then we notice this uses 2, so we need 2 more for this, so we put 1 here and 1 there. We cover this, it uses 2, so we need 2 more, 1 there, 1 there. So C2H4, all right? So let's look at butene, right? So but is 4, so that N is 4, right? So C4, and then 4 times 2, which is 8, right? So remember now, we need 4 carbons, right? We need 4 carbons, but one of these bonds need to be a double bond for it to be an ene, right? So let's put the double bond here, right? So in this case, we cover this one, and we get 1 already used, so we need 3 more. We cover this, 3 is used, so we need 1. We cover this, 3 is used, so we need 1. And then this 1 is used, so we need 3. Alright? Now, the thing with alkenes now is that they can act as a long chain as well, right? But their name can be specific. Now, specific means to tell you where the double bond is, alright? So instead of writing butene, alright, we can actually state which carbon has the double bond, right? And we do the same naming by seeing where which side the double bond is close to, right? So we call 1, 2, 3, 4, so it's on the second one. If we come from here, 1, 2, it's still on the second one, right? So therefore, we can actually be specific in the name that says it's a but hyphen, so on the second one, E, right? So this is a specific name of the structure, right? Well, let's say we had the double bond on this one here, right? It now is on the first. So in this structure, it would be but 1e, right? So the variation in name does not change the molecular formula, right? But it changes the structural formula, right? And these compounds these variations are actually called isomers, right? So it has the same formula C2, C4H8, but they have different structural arrangements. So that's what isomers are, right? So that's for the alkenes, right? And alkenes also can be branched, right? So let's look at the branch one. So let's say, all right, so let's look at a double branched alkene, right? So in this case, we know it's a double bond here, so it's an alkene branch, right? And we notice there is not one straight path that we can count all carbon from carbon to carbon, right? So there is a branch. So if we go 1, 2, 3, 4, that's our longest chain for that one. But if we go 1, 2, 3, 4, 5, 6, we get 6 from this, or 1, 2, 3, 4, 5, we get 5, right? So our longest chain is 6. Now the next part, right? So remember for alkenes is we count from the part that has the branch, right? But for alkene, we count from the part that has the double bond, it's closest to the double bond, which is not here. So we have to start from here. So this is 1, shows that the double bond is on 2, 3, 4, 5, 6, right? So now we know that this here is our branch, right? And our branch CH3 is methyl, so it's on the third carbon. So we start by saying 3 methyl, shows that the branch is methyl, is on the third carbon, right? And then we have 6, and 6 there is hex, right? So it would be hex, and we can state where the double bond is, and it's on the second one, which is hex2e. And that's how we name our alkene. Alright, now let's look to our alkynes. So alkynes now are the triple bonds between carbon and carbon. So we have one triple bond in our structure. Our general formula is CnH2n minus 2, and all their names end with YNE-ine, right? So let's look at as the first one, ethine, right? So this is our simplest structure. So we have 2, right? So this would be 2 times 2, 4, minus 2 gives us 2, right? So in this case, we have carbon, triple bond. We cover this, it has already uses 3, so we just need 1. Cover this, already uses 3, we need 1. So that's 2 C's, 2 H, right? Alright, let's go to butene. Now let's use pent, since we use but here. So we go pentyne, which is 5, so that's C5, right? 5 times 2, 10, minus 2, which is 8, right? So we go C, 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 so that's 5 C's. So remember, one of these need to be a triple bond. Alright, so let's go here, let's put it right there. So that's a triple bond there. Alright, so now we cover this as 1 use, so we need 3. Alright, so this one, if we cover these two, this one has already had 4, right? So we don't have any carbon there. If we go here, same thing applies, 4, right? So we go here now, 2 is there, so we need 2 more. Right, and our last one only has 1, so we need 3. Right? So just as alkenes, right, the position of our triple bond can be specific, right? So if we want to rename this in specific to our triple bond, right, it's the same as before. We come to the one that is closest to the triple bond, which would be from this side. So this is 1, 2, 3. So it's on the second one, right? So we would have pent, and we say it's on the 2, and then ine, right? So this gives us exactly where the triple bond is, all right? So, and the same process does apply for branching of our alkynes as well. All right. So, and also for the alcohols, right? Now the alcohols have their own formula. So we're just going to give you the formulas for the others, right? Because it's the same process in naming and also in drawing their structures.